All right, so today's quiz has been canceled, so we're not having a quiz. But I did plan on giving one, and it would have covered 1.3 and 1.4, at least the parts of 1.4 that we've talked about. So starting next week, I think you should be prepared for quizzes, at least one a week. All right.
It's supposed to be on 1.5.
Yes, but no. All right. I will talk about that handout in just a second. We need to finish up what we started last class. So there were two identities that or two limits that I said you need to know these. And I said the first one was super important. I told you that if we see a limit from here on out, if we see a limit and x goes to, it really doesn't matter what it goes to. If you have sine of some junk, right? That's what I called it? Some junk there, and then over the same exact junk on the bottom, that limit would be 1 so long as the junk was headed to 0, right? And also that junk and that junk have to match, like they have to be exactly the same expressions. Now, I'm going to add something to this. This limit also works if you flip the entire fraction over. So if you have junk on top, and you have sine of some junk on the bottom, this is also 1. So long as this junk and this junk are exactly the same and they both go to 0. All right? So with this particular limit, we can see it either way. All right? Now, the second limit is the same sort of thing. If this right here and this right here are exactly the same, and they both go to 0. So imagine that says cosine of junk minus 1 over junk. So long as these junks match, and as long as they both go to 0, the answer is 0. Okay? Is that all right? I told you you have to take these on faith. Now you may not flip this one over. If this one is flipped, it doesn't work. All right? Only that one. All right. Now, with that said, let's get into some examples. Y'all ready for the weekend? Anybody excited about the Super Bowl, or do y'all not care? No? No one cares? As long as you what?
As long as they get 3 and 5, I don't care.
3 and 5. Oh, yeah, bet. Okay, you got money on it. All right. Okay, here we go. First example. Find the limit as x goes to 0 of sine of 5x over tangent of 3x. All right, so we started talking about limits. Last class, we were talking about limits algebraically, meaning we're looking at functions now and we're trying to figure out the limit. We're not looking at graphs anymore, right? So this is a function. It's a sine function divided by a tangent function. And I want to know what happens as x goes to 0. All right, so if I replace this x with 0, that's 5 times 0, that's 0, right? And sine of 0 is 0. So we know that the top is headed to 0. And the bottom, we get 3 times 0, which is 0. And tangent of 0 is 0. So we have 0 over 0. Now how do you know the tangent of 0 is 0? Because you passed pre-cal. That's why you know tangent of 0 is 0, right? Okay, so if you need to review your trig functions, go back and review them. You should know what sine, cosine, and tangent, you should know their values at all the common angles, especially 0. All right, so what do we see whenever we have this situation, 0 over 0, what are we thinking?
Bad.
It's bad, right? And so we need to do some sort of algebra, right? So since we need to do some algebra, we can't do any factoring like we did before, right? Factoring, because this doesn't factor. I mean, you can't factor that. So we're left with really not a whole lot of stuff. Now, please tell me you're not going to cancel these x's, right? You're not going to do that? So whatever's inside this trig function, whatever's inside that trig function, they are trapped. You're not allowed to pull you can't pull a 5 out. You can't pull a 3 out. Those are major mistakes, right? So we are stuck with that. So you ready? Here we go. I'm going to show you how to do this. I'm going to rewrite this. And you just kind of follow along and tell me whether or not what I'm doing is legal or not. So, and you'll see why I'm doing it in a second.
Are we going to give you any promises this time?
Pardon me?
Are we going to give you any promises this time?
Promise? We might. We might. If I ever cancel something, I have to make a promise, right? That thing I cancel is never 0. Or sorry, yeah, yeah. So like, remember when we canceled a factor like x minus 2?
Which is basically a hole, right?
Is a hole. Yeah, it's a hole. Exactly. Yes. And we do have a hole in this graph. We do. At 0, this function is undefined.
Yes.
But it's, you know, what's happening is we go towards 0. Let's do something real quick. I'm going to go here, bring up graphing utility, bring up Desmos. Let's graph this function just to see what it looks like. Sine of 5x over tangent of 3x. All right, that's a mess, isn't it? And I want to know what's happening as our function approaches what? 0. So here's 0, right? On the x-axis, if we approach 0, from both sides, you can see the graph is headed somewhere, right? Both sides. It's headed towards something, isn't it? Now, at 0, we know that we have a hole, right? We have a hole there. The graph doesn't show us that, but we do have a hole. So it appears that this limit is going to exist, right? We're going to have an answer, but we have to figure out what it is. All right, so the first step here, what I did was I peeled these apart as two fractions. That's the same thing, right? That's the same thing. Now what I'm going to do is I'm going to go a little bit further, and I'm going to rewrite tangent in terms of sine and cosine. Because we did that a lot of times in pre-cal. Whenever we had something with tangent, we wanted to kind of like work with it, we would turn it into sine and cosine. So what would 1 over tangent of 3x turn into in terms of sine and cosine? So tangent of 3x turns into sine 3x over cosine of 3x, right? Sine over cosine. But that cosine can flip up. So we really have here cosine of 3x over sine of 3x. That's cotangent, basically. You could rewrite this. That's what I was going to say next. Just if you're having trouble with that, that's cotangent x. 1 over tangent's cotangent. And cotangent, by definition, is cosine over sine instead. We good up to there? Okay, now what I'm going to do is I'm just going to run through the limit again. All right, I'm going to run through the limit. As x goes to 0, what does this go to? 0? 0 divided by 1, is that bad or not? No, 0 divided by 1 is 0, right? Okay, so that's not a problem. Here, if we plug in 0, we get what? 0 here. So cosine of 0 is 1, right? And then sine of 0 is 0. And that's bad, isn't it? Because we have division by 0 here. So what I'm doing is I'm trying to isolate. This is the piece of the expression that's causing the problem, right? That right there. So I'm going to go one more step. Again, just follow along. This is the first example, so I kind of have to show you first. Then after that, hopefully you'll start to pick it up. So now what I'm going to do is I'm going to peel it apart one more time. Okay, so all I did here was cosine over sine. I could split that up as cosine 3x over 1 and then 1 over sine 3x. We all good with that? And remember, this is the part that's causing the problem, right?
Yes.
That division by 0. If I take this limit, this is 0 over 1, that's okay. If I take this limit, it's 1 over 1, that's okay. I do this one, it's 1 over 0, that's a problem. So now I need to come in here and somehow fix the problem. Right? You ready? It's going to be kind of weird. You ready? Using the property that I showed you, junk over junk, that thing I just showed you, right? What would we love to have had up here? A 3x. Wouldn't it be awesome if that one was a 3x? Because if that one was a 3x, then we would have sine of junk. 3x would be here. It would be the same junk, right? And then the junk would be going to 0, because as x goes to 0, 3x would be going to 0. So imagine, if you could right now, that there is a 3x right there. And don't write it down, but let's just imagine. If that was there, then what would this limit be? 1, right? And then we wouldn't have any problems. This would go to 0, this would go to 1, and this would go to 1. And so you'd have 0 times 1 times 1, and your answer would be 0. If there was a 3x there. But there's not, right? There's not a 3x there. So I'm going to make one appear. Right? So I get to come in here and I'm going to force a 3x to be here. And the way I'm going to do it is just be clever. I'm going to multiply the top and bottom by 3x. So that's a 1, isn't it? And since this is multiplication, aren't I allowed to now take this and just slide it over there to that? Right?
Yeah.
Okay. So let's see where we are now. Here's where we are. We have limit x approaches 0. We have sine 5x over 1. We have cosine of 3x over 1. We now have 3x over sine 3x, right? When I slide that over, we know all of those are good, aren't they? But what do we still have? The 3x on the bottom, don't we? So we say times 1 over, because we slid that 3x over, we still have 3x down here. Y'all see that? So this is good. This is good. This is good. This is bad, right? Because now we have division by 0. So it's like, I always imagine some poor guy in a canoe in the middle of the ocean or something. He's plugging a hole. There's like water coming. He's plugging a hole, and he plugs it, and then water starts coming in over here. So it's like we plug the hole here, but then we now have a new hole. Does that make sense? So how can I fix it? How can I fix it? This is a tricky move right here. How can I make that 3x not hurt us anymore?
Multiply by 3x. Yeah.
If I divide by 3x, I have to multiply by 3x, right? I don't know if that's what you mean.
Okay. Can we do it again? Multiply by. Oh, never mind.
So if we do 3x over 3x again, they'll cancel, but you'll still have a 3x here, right? All right, so you ready? This is fun. This is fun stuff. You see that x right there? Okay. That's a make. That's a make. All right. See that x right there? Okay, I'm going to do something with that x. This is all multiplication across the bottom, isn't it? Okay, I'm going to take this x, and I'm going to drop it off right underneath that. Right? Follow that? Now, why am I doing that? Well, if this is an x under here, then it's almost perfect. It's almost junk over junk again, right? What would I really need here, though, for it to be junk over junk? 5x, right? Well, what if I grab that x and slide it down here, and then introduce another factor out here, 5 over 5. Right? Now, if I do that, can't I take the 5 and slide the 5 out under here also? what would my new limit look like if I do this? I'd have sine 5x over 5x, right? Because I grabbed the x and slid it down. I grabbed the 5 and slid it down. And then I have cosine of 3x over 1. That didn't change. 3x over sine 3x. That didn't change. Times what's left right here? What am I left with right here? 1 over 3, right? And then what am I left with over here? 5 over 1, because I slid the 5 down, right? So this is 5 over 1. I realize this is weird, okay? I realize the first time you see this, this is strange. This is not, you actually have to like massage this thing into what you want it to be, right? So let's take a look at what happens. Let's run the limit through all this. What's the limit of this? 1. So that's okay now. I mean, it was okay to begin with, right? But it's still okay. This one's going to go to 1. This one's going to go to 1. This one, both of those don't have x's anymore, right? So you don't have that division by 0 anymore. You have 1/3 times 5. So that's it. This is our answer. It's 1 times 1 times 1 times 1/3 times 5, which is 5/3. If you've never seen something like that, that should kind of bother you, but it should also kind of give you your first glimpse into the strangeness of these types of limits. Let me bring that graph back up. Did it look like it was headed towards 5/3? Let's see, here's the picture. 5/3 is about 1.7-ish, 1.6. So this is 0, here's 1, here's 2, so 1.5. Yeah, that looks about right. That's headed towards 5/3 from both sides. Now, inevitably, somebody's going to say, well, couldn't we have just seen 5/3 here, right? And just write the answer down without doing any of that? Go for it. See how that works out for you. Don't do that, okay? You'll get yourself in trouble that way. I mean, you'll do a problem that it doesn't work that way, and then it'll be wrong. Okay, so the idea behind this is to see, can you introduce these factors? Can you figure out the ones you need to put in here to make this thing work out? Yes? Questions? I should probably do another one, huh? So let's see, how about... find the limit as x approaches 0 of (3x squared) over cosine squared x minus 1. Yeah, I like that one. Pardon? Oh, is the x minus 1 in the cosine, or is it by itself? It's by itself. So this has a parentheses around it. Had it been, had I wanted the 1 in there, then I would have needed to have put parentheses around that. So without the parentheses, it's understood that that 1 is separated from the cosine. All right, first thing we do, Emily, where's Emily? Emily, I didn't call on you last time, right? Okay, good. So Emily, what's the first thing we do with limits all the time? Yeah, just plug in and see what happens. So what happens up top, Emily? You get 0 on top, okay? All right, Emily, you're going to keep going. So if I plug 0 in here for this, right? Then what are you going to do first here? If I plug 0 in here, are you going to do cosine of 0, or are you going to square something first? What do you do? Cosine. All right, so what is cosine of 0? 1. Okay, so if you don't know that, if you're sitting there and you don't know that, again, you need to make sure that you get very comfortable with all those trig functions at the common angles, especially at 0. All right, cosine of 0 is 1. 1 squared is 1. 1 minus 1 is 0. So we have 0 over 0. That's bad. We got to do some algebra, right? Some sort of algebra. So I'll take a volunteer at this point. I don't want to call on anyone. I don't think it's very fair. You've got to be willing to take a swing at this, okay? You've got to be willing to try something.
Can you separate 3x squared into 3x and x?
Can you separate 3x squared into 3 times x times x? Is that what you said?
Yes, sir.
Sure.
And then cosine x squared, which technically,
This right here, what do you want to do there?
can you make that cosine of x and cosine of x minus 1?
Oh, like cosine times cosine, then minus 1?
So is it cosine squared or is it cosine x squared?
So when we see this notation, everyone, what this means is that. This is the notation for this. Which is why when I was asking Emily what happens first, you plug x in, cosine gets that first. Sorry, you plug 0 in, you cosine of 0 first, then you square the answer. All right,
Would that be tangent squared?
where's that?
Cosine squared x minus 1?
Is it, are you saying, is it tangent squared? I think you're mixing it up with one of the other trig identities. But there is a trig identity I may be able to use for that. Sine squared? So let's see, what is that? We have that Pythagorean identity. This was one of the really big ones from pre-cal. Hopefully you know that. Okay, so we have that equation right there from pre-cal. Is there any way I can make that look like cosine squared x minus 1? Can I move this 1 over? And that would make minus 1? But then I'd have to bring the sine squared over here, right?
Yes.
And it would become negative, wouldn't it?
Yes.
So the bottom I could write as negative sine squared x. Agree with that? Just move the 1 over, move the sine squared over. So I'm okay with that. Now, why would you want to turn the cosine squared x minus 1 into something with sine squared? Those sines, the sine junk stuff, those are the things that turn into 1s, right? So I'd love to work with some signs here if I can. What next? So far, y'all are doing fine with this.
Could this be sine times sine?
Yes, sine times sine. So why don't we do that? Limit x goes to 0. We'll leave 3 times x on top. And then we'll make it negative sine x times sine x. That's right. Now what?
2 junks?
You have 2 pieces of junk.
Yes.
Look, limit x goes to 0. Watch the way I write this. 3 over negative 1 times x over sine x times x over sine x. I'm just playing with fractions. That's all I'm doing here. As long as you agree that this is the same as that, right? That if I put this together, you would get that. Then that is a way we could view that expression, right? Sine junk, junk. Identical junks, right? Identical junks. Are these junks going to 0? Yes, limit goes 0, right? Sine junk, junk. This goes to 1, this goes to 1, that goes to negative 1/3. I'm sorry, not negative 1/3, negative 3, right? So this is going to go to negative 3 times 1, which is negative 3. Okay? When I first started teaching Cal 1, we didn't use this book. We used a different book. And the book that we used had at least 20 examples of this type of problem. This book, I think, has 4. I'm not a big fan of it because, not a fan that they only give you 4 problems because, I mean, these are really important types of limits because this is a type of thing that you don't normally see. Like in algebra, you don't do things like this. Pre-cal, you don't do things like this. And so you have to really like do repetition and practice to get good at it. Unfortunately, the book doesn't give you an opportunity to do a lot of practice with them. All right? But you're guaranteed, absolutely guaranteed to get something like this on the test without question. All right? Well, let's do another one. How about this one? Find the limit as x goes to, how about x goes to 4 of tangent of x minus 4 over x squared minus 16. Arafat? What's the first thing you always do, Arafat? Put 4 in for everything, for all the x's, right? Okay, so what do you get up top there?
0.
Tangent of 0 is 0, right? So we get 0 on top. How about the bottom?
0.
We get 0. Okay, what would have happened if we got 0 over 2? What if that would have happened? What would you do?
So x squared minus 16 root of.
Let's just say, I'm saying hypothetically speaking, let's say you would have got 0 on top and 2 on the bottom. What would you have done at that point? So is 0 over 2, would that have been a problem? No. So you would have got 0 over 2, and then 0 divided by 2 is 0, and that would have been your answer. You would have boxed it up, and you wouldn't have wasted any more time on the problem, right? Okay, let's just make sure we're all clear on that. Because I told you, don't forget that if your limit ever goes to something other than this, goes to a nice number, you're done. But that's not what happens. So we're bad. And all right. Anyone have any ideas?
Minus 4.
Okay, so the bottom is a difference of squares. How about we go with that? Okay, limit x goes to 4. We have tangent of x minus 4 over x plus 4 times x minus 4. Okay, there's our difference of squares. Okay, I agree with that. Now that does not get us around, well, please don't cancel those. Please don't cancel those, right? Why? This is inside tangent, right? It's not tan times something. It's tangent of something, and therefore these are not factors. This is not algebraically, it's not multiplication, so you can't cancel them. Although you may be tempted. Okay, anyone have any other ideas?
You could turn tangent into sine of x minus 4 over cosine of x minus 4.
So why in the world would you want to turn tangent of x minus 4 into sine of x minus 4 over cosine of x minus 4?
Maybe it'd be easier to factor it or work out. I mean, you could also probably turn it into cotangent.
So the formula we have with the junk in it, right, junk over junk, has sine in it, right? Yes? So maybe we should just get the tangent to get a sine, pop a sine out of it somehow. That way we can start working with our formula. And because, you know, at least historically, when we've taken tangent over to sine and cosine, it's always made life easier. So let me see. I don't know, maybe I'm stretching here.
And then once you do that, you can break them out even more.
Yes.
Okay, you're right, right.
Yep. I'm just like peeling everything apart. Okay, tangent of x minus 4 is sine of x minus 4 over cosine of x minus 4. I can write that with these two, right? So that's your tangent of x minus 4. And then we still have on the denominator these two factors, which I can peel off. I'm putting dots between these, right? I've created 4 fractions like that. I had a terrible morning this morning. Not terrible. It wasn't terrible for me, but I was going out in the front yard. My wife was leaving, and I saw my neighbor who has a dog, right? And he always walks his dog, and recently his dog had one of those Elizabethan collars on it, I guess. You know what I'm talking about? Something. No, it was. I think they had an injury or something. So I saw him. I was like, he had a different dog, and I was like, hey man, that's a new dog. And he's like, yeah. I said, was your other one, injured or something? Just kind of horsing around. He's like, no, man. His dog fell in the pool and drowned.
Oh.
I'm like, whoa. Like, what do you say to, like, oh, sorry.
So like
The new dog's cute. I mean, it was sad. He's all depressed. I mean, he had the dog for 16 years.
So did it drop? Did it have the collar or
No, the collar had come off. He had gone out of town. He had someone watching his house, and they didn't know, I guess, that not to let the dog out at night or something. I don't know. But he found it. He found his dog in the pool.
sue that person?
Well, I think he was a friend or something.
I mean,
Yeah,
regardless,
yeah, I know. You could be a lawyer or something. Huh?
Would it be
Thank you for bringing me back. Okay, no, I appreciate that.
would it be junk over junk if we were to move the x minus 4 over to the first?
Absolutely, that's what we're looking for. So if you come back and look at this, see how I've peeled it all apart? When you peel it all apart, you can identify the part that's bad. See, this part's not bad, because as x goes to 4, you get 4 minus 4 is sine of 0, 0. 0 over 1 is okay. Right here, cosine 4 minus 4 is 0, cosine of 0 is 1. 1 over 1 is okay. Right here, let x go to 4. It's 1 over 8. That's not bad. This is the part that's bad, right? This is going to give you a division by 0. So is there anything we could do with this? And then we kind of like go, holy crap, look, that's the same as that. And if we move that underneath, we got junk over junk, we're good. So that's exactly what we're going to do. We're going to identify that this factor can be slid over right there. And then we're in business. So I feel like I want to go like get a little basket or something for this guy and leave it on his front porch, and be like,
Sorry, you have shitty friends.
I don't know. I just don't know what I want to say. That's the thing. Do you give him like doggy treats or something? I don't know. Like, what do you do? Like, my condolences. He's a real nice guy, so I feel bad for him.
I mean, I think the best thing you can do is just ask him if there's anything I can do for you to make this transition easier.
All right. We're good? Sure? No questions? Yes?
So for all of these, is there like one way of doing it? Because whenever there's like other ways, then you're not going to mess up.
Yeah. The question is, like, is there one way to do all these?
Yeah.
And I guess my short answer to that would be no. I mean, every one of these you just have to start like kind of peeling them apart, trying to find things. It's not. I think this is what starts making calculus get harder or get difficult is that it's not just me showing you like very robotically, like do this, then this, then this, and then everyone just kind of mimics me. Like you have to think about this. You have to look at what's going on. You have to peel things apart. Exploit the weakness within the problem, right? The weakness of this problem is that this thing can be a 1 if that junk's going to match up. So I exploited it. What's the answer? If I take the limit now, right? This is going where? 1, 1, 1/8. 1/8. All right, I think maybe, let me see what the book has for you for this. I know there's one problem in the homework that's just a monster. Where is it? Oh yeah, this one. I think I do this one in the homework. You know what? I think I do it in the homework, so I'm not going to do it here. All right, I'm moving on. Yes?
So you said that on Canvas you provided some like formulas and stuff. Do you have like the identities so you can start memorizing them again on there?
Okay, so on Canvas, in Canvas, let me just take you there. Let me take you to Canvas. Ah. I just had to change my password this morning, so let's see. And Spring Cal 1, that's us. So if you go to Canvas, I'm just going to leave all that stuff up there. You go to Files, and over here you'll see Formulas. See that? Click on that. I would download it and print it. This has everything you're allowed to have on the test. So you have all your geometry. There's algebraic formulas. There are geometry formulas. So there's difference of squares, sum of cubes, difference of cubes. Next page is trig. So there's all your sine, cosine, tangent, your Pythagorean identities. They're all here. So these are all available to you during any test. But you should start to become like comfortable with this formula sheet. Like there's 6 pages of formulas you're allowed to have. Now a lot of them you won't need. Like you actually only need the first. For this entire class, you would only need the first 5. Okay, so you need 5 of the 6. Right. Does that kind of address your question? All right. All right, we're moving on. Now, your schedule says we're supposed to start 1.5 today. But I forgot when I made the schedule that I like to do 1.6 before 1.5. So we're actually going to do 1.6 today. And I apologize for those of you who may have watched the 1.5 course video before, just oops. Now, the reason why I like to do 1.6 before 1.5 is because 1.5 is kind of like a completely different topic. And then in 1.6, we go back to doing limits. So I think it just flows better if we just continue doing limits. All right, so we are now going to talk about limits involving infinity. Limits involving infinity. So maybe before we begin, we should just all make sure we understand, the idea of what infinity is. So infinity is not a number, right? We all understand that? Infinity is not a number. Infinity is an idea. If I say, hey, we're going to let a number get really, really big and just keep getting bigger and bigger and bigger forever and ever, then we would say that that number is approaching infinity. And the same thing with negative infinity. If we say negative infinity, the number is getting really big, but it's negative. So on the number line, infinity is the idea that we're going to go out that way forever, and negative infinity is the idea that we're going to go that way forever. Now, in terms of a function's value, if I tell you that a function's value is becoming infinite, that means when you graph it, it's going up to infinity, right? And if it's becoming, if a function's value is approaching negative infinity, it's diving down, yes? All right, so first thing we're going to talk about, and there's 2 separate concepts within this section. The first one is what we call infinite limits. And that means that we're going to see what happens when we take a limit and we get infinity as an answer. So here's a graph. And we've kind of talked about this already. We've seen this graph. I call this the volcano function. This is the function f of x equals 1 over x squared. You can see it right there. But that's the function, f of x equals 1 over x squared. Now, if I ask Aaron, where's Aaron Cagle? Aaron, if I ask you what f of 0 is here, what would you tell me? If I ask you to plug 0 into this function, what would you say? Which is? Undefined, right? So this will be undefined. undefined. And we can see in the graph that's at 0 you don't have anything, right? All right, but now we can ask the question, what is the limit as x approaches 0, no plus or minus, so that means from both sides, of this function 1 over x squared? So by looking at the graph, can you tell that as we come into 0 from the left-hand side, that this thing, the function is approaching positive infinity? And from the right-hand side, it's doing the same thing. So in this case, we would say that this limit is infinity, positive infinity. Because from both sides, the function is headed towards infinity. Does that make sense? I see some like, we're okay? All right, so this is what the function's doing as we approach 0. When we get to 0, it's undefined. Right? When we get to 0, it's undefined.
So it feels like opposite the lines, they're like down.
Down, down?
Yeah.
Yes, it would be negative infinity. Let's take a look at the next example. Well, let's look at this one visually. Nas, you're up.
Yeah.
Nas, what would f of, this is the function 1 over x, not 1 over x squared. So 1 over x, what is f of 0, Nas? Is it still undefined?
Yes.
It is still undefined. Plug 0 in here, it's undefined. Now, I'm going to stick with you, Nas. Just, what do you think? For 1 over x, what's the limit as x approaches 0?
I would say undefined, but I don't know why.
Okay, so as I approach 0, what's happening, Nas, as I approach 0 from the left? Where's the function headed? Where's that? What is that? Negative infinity, right? And then from the right, the function is headed towards positive infinity. And do you remember we said that for a limit to exist, they have to be going to the same place? Well, same thing works with infinity. If from both sides we're going up to infinity, then we can say the limit is infinity, just like the previous example. But if one side goes up, the other side goes down. Oops, got it the other way. One side goes down, the other side goes up, right? They are going to different places. And therefore, we will say that this limit, we don't say undefined, we say does not exist. D-N-E, does not exist. So always reserve does not exist for limits, and only use undefined when you're trying to plug numbers into a function. All right? So this limit would not exist because from the left and right, you go to two different places. Does that make sense? All right, so let's scroll back up. Blah, blah, blah. So what about if we look at this one, and instead of me asking you this, Raisul? Where's Raisul? Did I say that right? Raisul? What if I ask you, what is the limit as x approaches 0, but I put this here?
Okay. So if you go like that from the left side,
From the left side, where's the function headed as I approach 0?
down.
Down, and where's that? What do we call down there? For negative infinity, right? Negative infinity. So look, from the left side, this limit does exist. From the left side, it exists. What about from the right side? What's the limit as x approaches 0 from the right of this function? That's positive infinity, right? So these two limits exist. We call these one-sided limits. You're only coming in from one side. So the left-hand limit exists, the right-hand limit exists, but the limit does not exist because that covers both sides, right? So that's what this says right here. From the left, we're negative infinity. From the right, we're positive infinity. And the limit without the plus or minus means we have to check both sides, and therefore it doesn't exist because they don't match. Now, do you remember talking about vertical asymptotes in college algebra? Vertical asymptotes, when we would graph rational functions, we had these vertical lines, and they were like these barriers, and our functions would come up to them and have to like go up or like go down, something like that. Well, we can start referring to vertical asymptotes using limits for definition. So this says that the line x equals a. So x equals a is a vertical line. the line x equals a is called a vertical asymptote of a function if any one of the following are true. If any of these things are true, then we will call x equals a vertical asymptote. So this first thing is saying what?
As the limit approaches negative.
Okay, so this one is saying when we're on the function f and we're moving towards what?
From the left side.
A from the left side, if our function takes off to infinity, then we have a vertical asymptote there. So if you're coming into your function and it starts doing this, then we call that vertical line a vertical asymptote. If that happens, just one side, then we call it a vertical asymptote. Who cares what's happening on the other side? Or this could happen. We come in from the right and it goes to infinity. Or if we come in from the left and it goes to negative infinity. Or from the right it goes to negative infinity. Or from both sides it goes to infinity. Or from both sides it goes to negative infinity. All of these cases would qualify as a vertical asymptote. Any one of these things happening and we would call it a vertical asymptote. So I think I did a graph a while back in class, and it went like this, and then on this side I think it went like that. And someone asked me whether or not this would still be a vertical asymptote. Was that you? Yeah. And I think I said yes. I hope I did say yes. But this, let's say that this was our x-axis. This was our y-axis. Let's say this was 2. Then we would say from this picture that x equals 2 is a vertical asymptote. And the reason why we would say that is because the limit from at least one side, right? From at least one side of that vertical line, it's headed to infinity. So that vertical line qualifies as a vertical asymptote. All right? Even if I fill this in with a dot, it's still a vertical asymptote. So I say I will start using VA anytime I want to abbreviate it. All right, so here's some more pictures. So there's a vertical asymptote, right? There's a vertical asymptote. That's what I just drew, right? We have a vertical asymptote here because from the left it goes up to infinity. All right, any questions on that? You all right?
So on the test, how would you want us to write that?
For what? For vertical asymptote?
Yeah.
If I give you a function, say, find the vertical asymptote, you would say x equals whatever. All right, I think maybe before we move on to the next one, the next idea, we have to do some examples because everything I've done has been purely from pictures. So let's do this. Okay, find the vertical asymptotes of f of x equals 2 plus x over 3 minus x. Now, we can answer that question without any calculus at all. So how could I determine where the vertical asymptotes of that are? Anywhere where the denominator is 0, right? If we have the denominator being 0 and the numerator not being 0, then we have a vertical asymptote. So where would that happen? At what value of x do we have a denominator 0? At x equals 3. Okay? At x equals 3, we have a vertical asymptote. And that's because when we plug 3 into the function, we get 5 over 0, don't we? And so from what we learned in college algebra, if your denominator is ever 0 and your numerator is not 0, then you have a vertical asymptote there. But like I said, that has nothing to do with calculus. So now let me ask you some calculus questions.
So if anything is undefined?
You have to have undefined but not a whole. not a whole, okay? So that's what I was saying. If you can find the vertical asymptotes pretty easily, if you can figure out where the denominator would be 0 while the numerator is not. So if we get something like this over this over 0, or a number over 0 like that, then that is a vertical asymptote occurs there, all right? Just by looking at it. Let me try and illustrate just to make sure you understand that. Let's say I give you this function here. Does this have a vertical asymptote at 2?
It does not.
It does not.
Because it has a hole.
It has a hole at 2. So if you come in from both sides, you're going to go somewhere, and then you're going to have a hole there. Okay? So there's a big difference between this and that. Okay. Now, let me ask you the calculus questions. The only interesting point here is at 3, because 3 is where things get all jacked up in this thing, right? So find the limit as x approaches 3, and let's go from the left-hand side of that function, 2 plus x over 3 minus x. You all ready? Deep breath. Here we go. Karen? Where's Karen? Don't look so eager, Karen. Karen, what's the first thing we do when we do a limit? Just plug in, right? See what happens? Okay, so what happens if I let x go to 3 here, Karen? What do I get on top? Pardon? 5. And then what about the bottom? 0. Okay. Now, look at the sheet I handed you today. There's lots of different things that can happen when we take limits. I know it's hard to see this, but do you see that first box in the top left? It says 0 over 0, infinity over infinity. It says 0 times infinity. It says infinity minus infinity. It says 1 to the infinity. It says 0 to the 0, and it says infinity to the 0. Do you see all those? Okay. Anytime we ever see anything like this, when we take a limit, we are going to do what? Some algebra or some trick, right? Okay, now the only thing we've done is that one. Stay tuned. Stay tuned. We have a lot more to do, all right? But right now we know when we see 0 over 0, you do some algebra. Okay. Now, what if this is not 0 over 0, is it? This is not 0 over 0. This is 5 over 0. So this doesn't fall into that top left category. What category does it fall into? Well, the next one, the top right corner, says 0 over a fixed number. Do we have that scenario? No, we don't. And what is the answer if we ever see 0 over a fixed number? This is going to be 0 so long as what? So long as that down there is what? Not 0. Fixed. I'm saying if you see 0 over a fixed number, as long as that number down there is not 0, then the answer is 0. Because if it's 0, then you're back here. So look at the bottom. Do you see on the bottom where I put here fixed means non-zero and or bounded? So when you see the word fixed in this sheet, I'm telling you that that is a number, but it's not 0. Okay? So anytime we see this, like if these were flipped over, right? Our answer would be 0. But they're not flipped over. Okay, so it's not the top right. What about the left bottom corner there? It says if you have a fixed number, right? See that little plus sign right there? Over 0 plus, what's the answer? Infinity? Do you all see that? And then there's 3 more, right? Fixed. Negative over 0 negative. This is also infinity. Then we have fixed positive over 0 negative. That's negative infinity. And then finally fixed negative over 0 positive equals negative infinity. I'm going to explain this, okay? When we look at this 5 over 0, out of everything on this sheet, this falls into the bottom left box more than anything else, right? We have a fixed number, 5. divided by a number 0, right? So we have a fixed number over 0, fixed number over 0. So the question for us now is which one of these 4 is it? Okay, which one of these 4? Now you see this little plus and minus here. What this means is the number up top positive or negative? So 5 is positive, isn't it? So we're either looking at this one or that one, right? Y'all understand that? We have a fixed positive number on top. The bottom is headed towards 0, isn't it? But is it headed towards 0 positive or is it headed towards 0 negative? Let's see. What are we approaching? What are we approaching? 3, right? From which side? Okay, so imagine a number line right now. Okay, here's the number 3. I'm approaching from this side. So as I approach, I'm plugging in numbers that are closer and closer to 3. Somebody give me a number that's really close to 3, but on the left side of 3. 2.99. Does everyone agree that's 2.99? Would be there? I could go 2.999. 2.99999, right? Just more 9s, right, Chris? We talked about this. So if I start plugging that number, 2.9, in here, do we agree that 3 minus 2.9 will be small? And 2.999, plug that in, and it's going to be really small. And it's getting closer and closer to 0. But the question is it getting close to 0 being positive or negative? So think about it. 2.99 right here. What's 3 minus 2.99? Is it positive or negative? It's a positive number, right? 3 minus 2.99 is a positive number. So this is approaching 0, but it's approaching 0 through positive numbers, not through negative numbers. Does that make sense?
That's because we were going from the
That's because we were going from the left. The next example, I'm going to come in from the right, okay? But it's because we're coming in from the left that we're plugging in 2.9. When you plug 2.99 in here, you get a positive number down here. So you have a fixed number over a number that's approaching 0. Both of them are positive. Let me say that one more time. You have a fixed number over a number that's approaching 0, and they're both positive, right? That's this case right here. And the answer then is what? Infinity. But why? Why? Just do the math, okay? Let's take a number. Let's take the number 5, and let's start dividing it by small numbers. Because these are getting smaller, right? So let's divide it by a small number, 0.1. What's 5 divided by 0.1? That's going to be 5. 5. You're right, 50. 0.5. 0.1 into that is 50. Okay? Let's take 5 and divide it by an even smaller number. What's that going to be? 500. Let's go even smaller. 5,000. So do you see that the denominators are getting smaller and they're getting closer to 0? And that means the ratio blows up. I can't overemphasize how important this is. If you have a fixed number on top in a numerator, it's fixed, not moving, and your denominator gets small, the ratio gets big. Fixed over something getting small, the ratio gets huge. And that's why it's headed towards infinity. All right? So the answer to this problem right here, the answer to this, the limit as x approaches 3 from the left is infinity. Because that's what's happening. There's not, see, do you notice I'm not doing any algebra? I'm not doing any sort of like, when we had 0 over 0, we're doing some algebra or some sort of like weird thing with sine and junk. But when we have one of these 4, there's no algebra involved. It's all about thinking about what's happening, approaching a number from a side, thinking about